Let's explore another popular data balancing technique, that is ADASYN. ADASYN is nothing but adaptive synthetic sampling. It is different from the other data balancing technique because it adapts sampling strategy based on the density of the minority class examples. It gradually increases synthetic samples in the region with low density, improving the generalization and handling the highly imbalanced dataset very effectively. So let's have practical as well as theoretical understanding of ADASYN. What is ADASYN? ADASYN is an adaptive synthetic sampling and is a data augmentation technique used in a machine learning to deal with a class imbalance problem. Class imbalance occurs when the number of instances in one class is much higher or lower than the instances in the another class, and this making it difficult for a model to learn from the data. But what is after applying ADASYN? ADASYN generates synthetic samples based on the data distribution of the minority class. With more number of samples generated in the area of feature space where the class density of that particular minority class is very lower. The adaptive approach insists that the synthetic samples are more representative of minority class and our model would be less likely to overfit. The ADASYN algorithm iteratively generates synthetic samples until the number of samples in the minority class is equals to the number of samples in the majority class. Consider an example of imbalanced data. Here we can see the class-wise data distribution is not equal. The number of samples present in class 0 is not equal to the number of samples present in class 1. Now let's see what is after applying ADASYN. After applying ADASYN, we have a balanced data. The class-wise distribution is equal. The number of samples present in class 0 equals to the number of samples present in class 1. Now let's see what are the steps that ADASYN perform to balance the data. Let's move on to the step-by-step details of ADASYN. In the step 1, consider the red samples belonging to the majority class and the blue samples belonging to the minority class. In the step 1, we calculate degree of class imbalance. This is calculated with the help of number of samples belonging to the minority class divided by the number of samples belonging to the majority class. We calculate degree of class imbalance represented by small d, which equals to ms by ml, that is number of minority class examples divided by the number of majority class examples. After calculating d, we check a condition. If d less than dth value, dth is a preset threshold for maximum tolerated degree of class imbalance ratio. If d is less than dth value, then only we proceed for the next steps that we perform in ADASYN. Now let's move on to the step 2. We calculate number of synthetic data examples that need to be generated for the minority class. We calculate the number of synthetic data examples with the help of this formula. The number of synthetic data examples, which is equal to G, equals to ml minus ms multiplied by beta. ml is the number of samples belonging to the majority class minus ms, which is the number of samples belonging to the minority class. And here beta plays very important role. Beta belongs to 0 and 1 and is a parameter used to specify desired balance level after generation of synthetic data. Let's take beta equals to 1. If we take beta equals to 1, then the number of minority class examples equals to the number of majority class examples. And if we take beta less than 1, the number of minority class examples are less than the number of majority class examples. And lastly, if we take beta greater than 1, then we have the number of minority class examples would be higher than the number of majority class examples. This is how we set beta value. Now let's move on to the step 3. In the step 3, for each example xi belonging to the minority class, we find k nearest neighbors based on the Euclidean distance in the n-dimensional space. And we calculate the ratio Ri, which is defined as Ri equals to Ni divided by k, where I running from 1 to m. Ni is the number of examples in the k nearest neighbors of xi that belong into the majority class, and Ri always lies between 0 and 1. Let's take an example where blue samples belong into the minority class and red samples belong into the majority class. Now let's focus on this ellipse. Here we can see the three samples, that is red samples, are from the majority class and the two samples are from the minority class, which is a blue sample. Ri is calculated by 3 divided by 5, where 3 is the number of majority class samples divided by total number of samples, which is 5. The Ri value is 0.6. 3 equals to the number of red samples and 5 is the total number of samples belonging to that particular ellipse. That ellipse is the number of neighbors belong to the selected minority class example. Now let's move on to the step 4, where we use this Ri value. In step 4, we normalize the Ri according to the formula Ri cap, which equals to Ri divided by summation of Ri. Shortly, we can say Ri is the proportion of majority class examples belonging to the nearest neighbors of that selected minority class example. We calculate number of synthetic data examples that need to be generated for each minority class example xi. With the help of this formula, gi equals to Ri cap multiplied by g. For example, let's take Ri equals to 0.6 and summation of Ri equals to 20. Then Ri cap equals to 0.6 divided by 20, which equals to 0.03. G is equals to total number of samples in the majority class minus total number of samples in the minority class. Consider G equals to 400 minus 100, which equals to 300. Here 400 samples belong into the majority class and 100 samples belong into the minority class. We calculate small gi equals to 0.03 multiplied by 300, where 0.03 is equals to Ri cap and 300 is a capital G. After calculating this, we get gi equals to 9. That is, we have to generate 9 synthetic examples for this selected minority class example. Here we generate 9 synthetic minority class examples for the selected minority class example. Now let's move on to the step 5, where we can see for each minority data example xi, we generate gi synthetic data examples according to the following steps. We perform or we do a loop from 1 to gi. Gi is the number of synthetic examples that need to be generated for ith minority class example. Consider this is our minority class example where we need to generate gi number of synthetic data example. We randomly choose one of the minority data example xzi from the k nearest neighbor for the selected data example xi. Consider this is our neighbor of that particular selected minority class example, and it also called as xzi. Now we generate synthetic data example with the help of this formula si equals to xi plus xzi minus xi multiplied by lambda. This is how we generate synthetic example on this line, or the line between the selected minority class example and its neighbor, where xzi minus xi is the difference in the vector in n-dimensional space, and the lambda is a random number lies between 0 and 1. This is how we generate 9 synthetic examples for our selected minority class example. 9 is a value of gi. This is the second minority class example or synthetic minority class example. This is the third, again fourth, fifth, sixth, seventh, eighth, and this is the last ninth minority class example or synthetic minority class example. This is how we generate nine synthetic minority class example for our selected minority class example. This is the synthetic example. We generate a synthetic minority class examples until the total number of minority class examples equal to the total number of majority class examples. This is the process that we perform for ith minority class example. This is how ADASYN works. ADASYN perform oversampling by using these particular steps. Now let's move on to the practical implementation of ADASYN in Python. We have already conducted modeling on data imbalance and also explored some techniques like random undersampling and random oversampling, and another is smooth and borderline smooth in the series of videos on data imbalance. The first video is on handling data imbalance using random undersampling and random oversampling, and the second video is about handling data imbalance using smooth and borderline smooth. In this video, we have covered what is data imbalance, what are the consequences of data imbalance, also a theoretical knowledge of each and every steps that we perform in these techniques to handle the data imbalance, and also have practical implementation of uh, handling data imbalance using these techniques, which is random undersampling, oversampling, as well as in the video of handling data imbalance using smooth and borderline smooth, we have covered practical implementation of those techniques. You have to visit that particular video because of we are going to use the same data set and this same Jupyter notebook for the ADASYN. So this is our data. The data is about handling data imbalance on the vehicle insurance data. The data set having two classes. Class 0 consists of these many samples of these many data samples, and class 1 having these many data samples. We have to build a model that predict whether a customer would be interested in vehicle insurance or not. So this is all about data. You can see from the distribution of the classes, our data is imbalanced data. So I will share the link of this data set as well as my Jupyter code notebook and the videos that the videos on the series of data imbalance, that is handling data imbalance using random undersampling and random oversampling, and another is video on handling data imbalance using smooth and borderline smooth. I will share all these in the video description, so able to access uh, all those things. Now let's move on to the main part. Firstly, we'll load our all the libraries that we required. So let's run this. This is our data. I'm going to use the same Jupyter notebook. That's why you can able to see this is a part of our previous videos. This is our data. It does not need ID column. So firstly, we drop our ID column. This is our data after dropping that ID column. Now let's see the class-wise data distribution on the original imbalance data. This is the class-wise data distribution on the original data, and this is the bar graph of our data. You can see the bar of class 0 is comparatively higher, much higher than class 1. That's why we can able to understand our data set is imbalance. Our data set contain three categorical variables, which is gender, vehicle age, and also vehicle damage. So firstly, we convert it into a number form with the help of label encoder. This is the processing that we have to perform on our data set. I have explained each and everything about these techniques or this pre-processing in the previous video, so I highly recommend to visit that video. This is the architecture that we use to train our data. So this is our model, and this is the function that we use to evaluate our model. So let's run this also. Now we'll load our model. Now we can go firstly we see the results. This is the results that we got after training our model on the original imbalance data. You can see the precision recall and F1 score for class 1, which is the minority class, is worst. Here you can see the precision recall and F1 score is 0. and the number of misclassified examples in case of class 1 are very big. So after applying undersampling, we have these results. So here you can see the precision recall and F1 score for the minority class, which is class 1, is quite good now. Now we can say that our model is well generalized on the unseen data. So after applying random oversampling, we have these results, which is also a good result. We also see, we also covered another technique, which is mode technique. These are the result after applying SMOT, which is also quite good. The number of misclassified examples in case of minority class is get reduced. And lastly, the borderline SMOT. These are the results we got after applying borderline SMOT. These also good results, and number of misclassified examples for the minority class is also get reduced. So these are the results we got after applying these 4 techniques. Now let's move on to the another technique, which is ADASYN. Firstly, we segregate our explanatory variables and our target variable. So let's run this. I will show you our explanatory variables. Let's see data.head. Okay, data.head. Here you can see this is our data, and response is our target variable, and the remaining columns are our explanatory variables. So firstly, we segregate it. After that, we are going to apply ADASYN on the training data only. We are not going to apply ADASYN on the testing data because this is the wrong way. So firstly, we apply ADASYN on the training data, that is X-train and Y-train. So let's run this. Now let's see the class-wise data distribution in our training data, that is X-train and Y-train. Here you can see the class 1 having 2,61,027 number of data samples, and class 0 having 2,55,642 number of samples. Again, we are going to normalize our training data, that is normalize our explanatory variables from training data with the help of min-max scaler. It's a part of sklearn library. Now let's run this. Our data is converted into a normalized form. Now we are going to train our model on this training data, that is X-train. We have to pass X-train and Y-train here. We have used batch size about 32 and number of epochs is 5. So let's run this cell. The model training process will take some time, so we'll meet after 5th epoch. Now our model training is done. Let's move on to the inference part. We take an inference with the help of this model on the testing data using nn.predict. Nn is our model and .predict is one of the class object of that particular nn class, nn model. So let's run this. Now we are going to evaluate our model using measure underscore accuracy function. Here you can see the accuracy of our model. The precision recall and F1 score for the both classes are quite good, and the number of misclassified examples in case of minority class, which is class 1, is also get reduced. Let's compare this result with other techniques as well as our original dataset accuracy. So firstly, go to our results of our original data. These are the results that we got after training our data on our original data on our model. So you can see this is the results. The precision recall and F1 score are quite worst in case of minority class, which is class 1. But after applying different techniques, we have good results. Here the techniques that we recently applied, which is ADASYN. This is the results after applying ADASYN, so which is quite good. And these are the results of borderline SMOT, which quite almost same. These are the results after applying SMOT, which again same with the other techniques. These are the results after applying random oversampling, and lastly, this is the result that we got after applying random undersampling. So we can say that we go with any of these method when we have to balance this data. But I will suggest, when you are going to balance your data using these 5 different techniques, firstly try these techniques one by one, and after that decide which method is suitable for your data. So don't go with only one method, just try different method, so you will be able to understand which method is suitable for our data. This is how the ADASYN handles the data imbalance. Thanks for watching. If you enjoyed the video, please subscribe my YouTube channel. Your support means a lot for me. See you in the next super exciting video.